Welcome to Graphing Trig Functions and Transformations Part 2. In this video I hope to clarify a few things from the previous video, correct a few things, add a few things. Basically I put a lot of comments to the video in Part 1 below the video, but they may have been hard to follow, especially without a video demonstration. So this is going to go kind of hand in hand and to visually illustrate a lot of those things. Alright, so the layout of this video, we're gonna go from fairly easy, quick and easy points to more important and slightly more complicated points. Alright, so quick thing number one. In part one, I referred to this vertical shift upwards. I didn't know the name at the time. It's called a midline shift in case you see it anywhere else. So this +5 where you move the curve up by 5 is called a midline shift. The midline, I would imagine, refers to the fact that in a sine wave there's a middle or symmetric part that goes through it, so you're literally shifting the center up by 5. So that's the midline shift. Alright, number two, I neglected to give you guys an example on y-axis reflections in part 1. So here's an example. Let's say you have your regular sine function, and instead of x, if you were to plug in negative x, the negative would mean you're reflecting everything across the y-axis. So the solid line represents the original function, and this dotted line represents the transformed one. So if you look at this top arrow, a point over here would go to the left. However, if you're already on the left, this point would now go to the right. So that's the way that works. And here's an example on the right with just some random general functions. So this solid line is the original, and we're just going to reflect this in our y-axis to get this dotted version. So that's the way that works. Alright. Number 3. Everything you need to know about the inverse of a function is going to be in a linked video. So in part 1, I sort of briefly and fairly confusingly mentioned that we can reflect a function across the y equals x line to find its inverse. And I think I attempted to explain that, and even in part 1, the comment section, I give a verbal description, but I've made a separate video where it tells you how to find it, why there is this y equals x reflection for the inverse, and basically everything you guys would need to know about the inverse. So there's a separate video which will cover everything on that, so please make sure to see that. That will help clarify a lot of things. Alright, number 4. So the major reason I'm making this video is I made a huge mistake in part 1. I'm really sorry, guys. Here's the mistake that I made. So this isn't the exact function I used, but the inside is the same. So it had y equals sine of 2 theta minus pi over 3. So we have both this 2 transformation going on and this pi over 3. And my major mistake is that I said that pi over 3 means there's going to be a rightward shift of pi over 3. Now, if this 2 weren't here, and it were just theta minus pi over 3, that would have been a correct statement, but it's not correct. So the fast way to see that it's not correct is just to see, well, what happens on the left. We have our original sine function, and let's see what happens to this point 0, 0 in this new one. So how do we make this whole thing 0? So we know that we need this input to be 0 because sine of 0 will be 0. And so what value of theta gets this to be 0? And of course it's not pi over 3 as I said, it's pi over 6. So the way to see that is to factor out the 2, and then you'll see that if you make theta pi over 6, these will 0 out, and then you'll have sine of 0. So that's when you see a number that's any number here that's not 1, make sure to factor that out of that second number so you can see the actual shift. So here on the right I have the diagram, so it's a rightward shift. So this point 0, this old point 0, 0 is now pi over 6 comma 0. So we've moved to the right, I'll just make a big arrow, by pi over 6. Now I just sketched a few other critical points over here, so our old points of 0, 0, pi comma 0, and 2 pi comma 0 have now become 2/3 pi and 7 pi over 6. How did I get these numbers? Well, I figured out this pi over 6, and since this 2 means that everything is compressed by a factor of 2, it means this move of pi is now going to be only a move of half a pi. So if If you add pi over 6 plus pi over 2, you should get that. If you add another pi over 2 to that, you should get that. All right. So so that's basically takes care of that. So make sure when you see both numbers here, you don't just think that that number is the direct move to the right or left. So this is not the true number. Now, I want to make a more subtle point, and this is going to relate to number 5. So does the order of transformations matter? So here we have this 2 and we have this pi over 3. So what do you do first if you want to draw it from the basic, if you want to basically take your original sine function and draw that one? Do you apply the 2 first, or do you apply the pi over 3 first? It turns out, and not many people actually I think know this, but you can do it in either way if you were to make a few changes. So method 1 would be apply the 2 first. In other words, compress your function so that instead of going from 0 to 2 pi for one loop, now it does that from 0 to pi. So you're going to do the 2 first. And then, as we said, the shift is not a pi over 3, but in this form we could see it's a pi over 6 that it's a shift. So you apply the 2 compression and then the pi over 6 to the right. That is pretty much the recommended method. The reason I recommend it, it's pretty easy to see because this point hasn't moved, and so it's nice to compress it around a very simple point. However, you could do method 2, which is take the pi over 3 as is. So you might be thinking like, hold on, you just said that it's not pi over 3, but hang in there. So apply pi over 3 to the right and then compress it by a factor of 2. So you might think, wait, that's going to be wrong. But this 2 is going to compress everything. So that pi over 3 that you just moved to the right will be compressed. So now you've only moved half of that. So you've only moved pi over 6. In other words, this 2 going second will correct the initial number. So this is going to turn out in the whole to be correct. So you can use either method 1 or method 2. The reason I don't recommend method 2 is once you've shifted your function off of 0, 0, it's a little harder to visualize how to compress it. But maybe not. Maybe, feel free to try it that way if you prefer. So either of these methods is fine. I'd probably use method 1. All right. So does the order of transformations matter? In general, it depends on the function that you're working with and on the transformations. So the short answer is sometimes no, it doesn't matter, and sometimes for these simple sorts of transformation, it may not matter, but only if you modify it. So it's only no with modification. So it's either yes or no, it depends, is the short answer. So here's an example where it doesn't matter at all. Let's say you have y equals square root of x minus 3 plus 5. So in this diagram, I've sketched it. So the square root basically function got moved to the right by 3. That's this minus 3 here. It shifted a 3 to the right. And that plus 5 at the very end, you moved everything up by 5. But notice we could have done this in 2 ways. We could have moved it up by 3, then by 5, or moved it up by 5 and then over by 3. So in this case, since these are moving it in different dimensions, one is horizontal and one is vertical, they're completely independent transformations, so we can apply them in any order. Whereas as we've seen with these two methods, if you're going to reverse the order, you're going to have to apply slightly different transformations. All right. So that's a major correction. I hope that was helpful. Finally, I want to end with this. So I know I made this mistake, huge mistake, as I mentioned, and I want to apologize again for the part 1 mistake, but every mistake has an opportunity. So since I've made this quote mistake, let's see what can we learn from this. So there's actually 2 good things that resulted. For both you guys and for me, we've both gotten, hopefully, a deeper understanding. So while I made a mistake, maybe before, without the mistake, I knew to do like one of these methods. Now I got a better insight and investigated a little more and saw like, wait, actually I can use any of these methods if I tweak the transformations a little bit. So that's kind of new for me. So I'm happy I learned that new piece of information. And for you guys, the really, really like high level thing, like outside of even math, is making mistakes is a normal part of the learning process. So, it's nothing to freak out about. I make mistakes, and I'm happy to an extent that you guys saw me make a mistake in part 1. Everybody makes mistakes, so don't feel terrible if you've made a mistake. The question is, what can you learn from it? So can you improve? Is there a lesson? Can you help somebody else because of it? So don't feel bad about it. So that's the really, really important point. So beyond the math, and I mentioned this in the comment, the same thing in the comment to the part 1 video, so you can read my comment there about this. But I really want to emphasize that every mistake is an opportunity to learn, some sort of opportunity. All right, I hope that was helpful. I'll see you guys in the next video.